Okay, so welcome to Recitation 6. To start, I know this recitation is recorded, but we are still trying to test out the potential ways to do this recitation, as we can potentially do this as recorded. Um, so first of all, I just wanted to ask people to visit this on their free time. This is a Google form, a survey for this recitation in general. So right after this recitation, feel free to edit the form. I'm also asking in general if people are capable of attending a recitation if I held it at the same time as my normal one. Um, but please do take the time to fill out this form. This link is very long, so it's in the stellar announcement, so you can just go to that link as well. But today we're going to cover nucleic acids and a start of translation. But before that, I wanted to first show you guys a quick update. In your stellar page, you should definitely check out the lecture schedule and the Zoom office hour schedules, and basically anything that was posted since spring break. They will give you the clearest detail on the material you need to know and the changes in this course policy. Here I have the schedule, for instance. This should let you know that the exam 2 should end on nucleic acids, so make sure to remember that as you start cramming. And that the material afterwards will cover in the third exam. So definitely make sure, I know I receive a lot of questions on what is exactly covered, so make sure you check those out. As usual, at the section called Joseph's Recitation, I will also post my notes and some sample problems later in this week. So make sure that you spend some time checking those out. If you have any questions on us, feel free to email us or go to the Piazza. The TAs will answer that. And then, but in general, feel free to ask us any questions. And definitely check out the link I sent on the survey. So if you have any suggestions on how we should do recitation, how we should do class, we are gonna do that. This recitation, by the way, will be uploaded in YouTube and the MITX website as well. So that way you'll have access to either one, and I will put those links in the seller announcement as well. So to get started, we left off with nucleotides and nucleic acids. So to kind of start off with some definitions, a nucleotide and a nucleoside are different in the phosphate. So a nucleoside is a sugar and a base, whereas a nucleotide is a sugar and a base with a phosphate. So this thymine molecule, if I only have the base and the sugar, that's a nucleoside. If I add a phosphate, that is a nucleotide. As you already know from intro bio, there is a difference in DNA and RNA in that DNA has thymine, whereas RNA has uracil. What you may have not known or put much attention in DNA before is the specific structure and the three-dimensional shape. So in terms of structure of the bases, I put in here a guide of the purines and the pyrimidines, where you'll see the structure. Remember, purines are 2 aromatic rings, pyrimidines are only 1. And it's helpful to have this on your cheat sheet. That way, if he refers to draw a guanine or a cytosine, you have that on your cheat sheet immediately. I believe in this course, it's not important to memorize the way the atoms are looking at, unless you're taking the MCAT. What's more important is knowing or understanding why it makes sense that, let's say, G and C are partners. And we'll go over that in a bit. One other thing to note is the three-dimensional shapes of DNA come in 3 flavors: aDNA, bDNA, and zDNA. So bDNA is what we normally have in our cells. The bDNA is the most compact, and it has the largest major groove. And what is the major groove? So if you look at this right-handed helix of a DNA molecule, there is this segment right here where my mouse is that is larger than this segment right here that is smaller. And if this DNA molecule continued on, it's an alternation of large and big, large and small, and large and small. So that large section right here is what we call the major groove. The smaller one is what we call the minor groove. And from here, what we notice is that the bDNA form, there's a larger major groove. In the same token, this minor groove is smaller. In aDNA, we have kind of a change. The DNA molecule is less compact, and that the major and the minor grooves are kind of evened out. One thing to also notice, the nucleotides in the aDNA form are not lined up perfectly, whereas the bDNA form has them lined up perfectly to each other. And this is actually important because lining up these aromatic bases lead to stability. Lastly, the zDNA form is if the DNA twists left hand instead of right hand. And what you'll notice here is that it's a completely wax structure. It's only really possible at high salt concentration. However, some scientists have said that they also found it during transcription, but its function is relatively unknown. So if you want to read more on the zDNA, you can look this up. But overall, all of our biology revolves around bDNA. One more thing to note is that bDNA is when you have a double-stranded DNA helix. Not relevant for this year of class because we are not covering transcription, but if you have a DNA RNA hybrid, such as when you're doing transcription, it actually does more of the aDNA form. So here I have just a quick picture of a string of nucleotides. One thing to appreciate is the directionality. On one end of this DNA string, you have the 5' end. On one end, you have the 3' end. And so, as you already remember from biochemistry or intro bio, DNA has a 5' to 3' directionality. We call this the 5' end because this is the 5' end of the sugar. If you notice our guide right here, the purines or the bases in general have the numbering 1, 2, 3, 4, 5. And to distinguish that from the carbons in the ring, we give it a prime notation. So this N has the 5' as its farthest carbon. This one has the 3' as that. And you guys know about the general canonical base pairing, AT and GC. So what's important to know is, one, when these are paired with each other, doesn't matter if it's AT or TA or CG or GC, they have the same width in the DNA. And what that does is it keeps DNA the same width throughout. So there's no bulges in DNA when it's double-stranded. And actually, that's useful because any kind of bulge in the structure of DNA tells proteins that it is a mismatch. And so it's important to have that same width. Hence, this is the perfect pairing. And what you should appreciate is how well the T and the A and the G and C line up their hydrogen bond donors and acceptors. Where there's an acceptor on one, there's a donor on the other part. And what makes them paired is that given the directionality of 5 to 3 on this end and 5 to 3 on the other end, their donors and acceptors line up perfectly. I would highly recommend that you draw your nucleotides in this form to save space instead of having them in a separated form. That way you not only see the base and what the structure is, but you also get to see it in its paired up form. It's very common for Yafi to ask a question to draw a particular base, and so it's important for you to just have them ready in base pair form. It also lets you know which parts of the nucleotide are involved in the canonical base pairing. Because if there's a canonical, there's a non-canonical, but these particular atoms, those are the ones involved in the canonical Watson-Crick base pairing. For base stacking and hyperchромicity, this is a continuation of the point we said earlier. In bDNA, bases are lined up perfectly. And the reason why is that stacking of these aromatic molecules lead to stability. Hence, the DNA molecule is more stable when it's in its double helix form. One potential question that might come up revolves around the way DNA denatures. So DNA, when it denatures, would mean that DNA separates from 2 strands to being a single-stranded DNA. And so in general, at low temperatures, DNA is expected to be double-stranded. At high temperatures, it's expected to become denatured or single-stranded. And the temperature at 50%, we call that the melting temperature, or the melting temperature of a DNA molecule. And in this graph, there's 2 things to notice. One is that the DNA molecule melting curve is sigmoidal, which kind of looks like the cooperativity curve, because it behaves cooperatively in the sense that once the DNA starts denaturing, it makes it easier for more of it to denature. The next thing is to notice is that the higher the GC content, the curve shifts to the right. What this means is that GC, we knew from earlier, has 3 hydrogen bonds. That means it's the stronger of the 2 pairings. Hence, the stronger the GC content, the more bonded the 2 strands are. Hence, it takes higher energy to separate them. Therefore, the melting temperature is higher. So if you can understand that from this curve, then you understand how DNA denatures in general. I put in here the general pairings of DNA that's possible. On the left are what's known as Watson-Crick or canonical. This is your typical GCAT. What you should appreciate is the distances between the C1 and the C1. Regardless of G or C or A and T, you notice that the distance from C1 here to C1 there is exactly the same as C1 here to C1 there. And as a result, you are capable of maintaining that width of DNA. On the other hand, for Hoogsteen and reversed Hoogsteen, those are the base pairings that are not using these canonical locations. As a result, you get weird base pairing at different locations. And the most important thing to notice, besides memorizing or writing down your cheat sheet what the particular pairings are, I want you to notice the distances between their carbon ones. They are no longer the same. And so we'll see this a lot in the future, but Hoogsteen base pairing is important when we are having base pairing that is not normally distanced. And so if you have a particular nucleotide binding to DNA in an awkward fashion, you might see a distance between C1 to C1 different from the canonical. Or if you have something like RNA that can fold onto itself, you can see a very close connection there. And so remember, Hoogsteen doesn't use the same base pairing patterns as Watson-Crick, and it's normally seen in a lot of self-folding nucleic acids. To leave off to that, the major-minor groove we talked about earlier. Let's start from the bigger perspective in here in the bottom right. You see a 3-dimensional DNA drawing, and you'll notice that there's a section that's large and a section that's small. The section that's large is called the major groove. The section that's small is called the minor groove. And we said earlier, the major groove is important because it allows us to read the DNA. So how exactly it does that? So the reason why DNA, when it forms a helix, it creates this major and minor groove is because of an asymmetry in the bond. So if we take a slice of this DNA and look at it from the top, we get this top screen right here on the upper right. If you put the sugar on the lower left and the sugar of the lower right there, you'll see that there's a side that's orange and a side that's yellow. The side that's orange is basically what's the major groove. And in the side that's yellow is basically what's the minor groove. And what's important here is that in the major groove, there's a specific pattern of hydrogen bond donors and acceptors. So for adenine and thymine, you have nitrogen, which is a hydrogen bond acceptor, and NH, which is a hydrogen bond donor.